So what are the Bohr's postulates for the atomic structure? There are three postulates, no? Postulates number one. There are three postulates. Number one, I Hashari bolto. Number one postulates কি ছিল? হর্ষদীপ হর্ষদীপ বল postulates কি ছিল?
প্রথমে ওই অ্যাঙ্গুলার মোমেন্টাম ইকুয়ালস টু nh বাই 2 পাই।
এটা প্রথম postulates। প্রেমাঙ্কুর postulates কি ছিল?
Sir, electrons are a particular specific stable orbit revolve করে যেটা
আচ্ছা, আর তার সাথে
তারপর যে অরবিটে স্যার অ্যাঙ্গুলার মোমেন্টাম mvr ইকুয়ালস টু nh বাই 2 পাই। n হলো মানে প্রিন্সিপাল কোয়ান্টাম নাম্বার।
দেন
আরেকটা ছিল হলো যখন ইলেকট্রন হায়ার অরবিট থেকে লোয়ার অরবিটে আসবে তো এনার্জি এমিট করে, আর যদি লোয়ার অরবিট থেকে হায়ার অরবিটে যায় তাহলে এনার্জিটা সাপ্লাই করতে হয়,
মানে বাইরের সোর্স থেকে এনার্জি অ্যাবজর্ব করে। যাই হোক, আমরা অ্যাবজর্পশনটাকে না বোর্ডসের পস্টুলেটসের মধ্যে ধরবো না, আমরা খালি রেডিয়েশনটাকে ধরবো। দ্যাট মিনস হায়ার অরবিট থেকে লোয়ার অরবিটে যদি জাম্প করে তাহলে এনার্জিটা হু ইজ বান্টি দত্ত? বান্টি দত্ত, হু ইজ বান্টি দত্ত? হই দেখি চ্যাংড়াটা কি? ওকে, বান্টি দত্ত। হু ইজ বান্টি দত্ত? হু ইজ বান্টি দত্ত? হু ইজ বান্টি দত্ত? হু ইজ বান্টি দত্ত? বান্টি দত্ত প্লিজ অর্ক, there is অর্ক, but who is বান্টি দত্ত? হেই, এই বান্টি দত্ত কে ছিল রে? ওই বান্টি দত্ত কে ছিল? দেবায়নের মধ্যে তো সবাই প্রেজেন্ট। তো বান্টি স্বর্ণজি চিনিস বান্টি দত্তকে?
না স্যার।
সে জয়েন করে গেছিল। ওকে, দেন আচ্ছা একটা কাজ করতো, আমি একটু এটা কি আমি বান্টি Hey Dipti, do you know the Banti Datto? Sir, मैं Banti. Who is Banti? No, sir. Okay. Then I asked to everyone how he that Banti Datta get my account, means the link of this class. Okay, leave it. Okay, So the postulates number one, the electrons revolve around around the nucleus only in certain permitted orbits. Okay, electrons revolve around the some permitted orbits. That's orbits are called the stable orbits. Okay, electron revolves around some permissible orbits whose radius are fixed. That means suppose this is a nucleus. It's a very wonderful. It's a nucleus. Suppose this radius is 0.56 Armstrong. This distance. So with this distance you draw a circle. This orbit is not allowed. Only 0.53. This radius is allowed. Okay, so 0.56 is not allowed. Then something different. Then something different. So there are stable orbits having a specific radius. These orbits are called stable orbits, and they are defined by the principal quantum number n, and n is equal to 1 is known as first orbit, which is actually ground state, designated by k. For n is equal to 2, it is defined by the letter L, then 3 is defined by M, and so on, A, L, M, N, O, P, etc. So first principal quantum number, second, third, fourth, fifth, etc. orbits. This is the first orbit, second orbit, third orbit. And you know that in your earlier classes, number of electrons in any stable orbits, maximum number of electrons is 2n square. So this is the total number of electrons can exist in any stable orbits. Okay, this part is not our concern. Only we just denoted the letters to the orbits. First orbit with the letter K, second with the L, third with the M, and so on. K, L, M, N, O, P, etc. There are 7 orbits maximum. There are 7 orbits. That's why in the periodic table there are 7 periods. Okay, so this is the postulate number 1. Postulate number 2 is if an electron exists in any orbit, that means if an electron revolved around the nucleus in any orbit, in any stable orbits, then in the first orbit you have to added this other portion, that when the electron revolve in any orbits, electron cannot radiate by itself. Okay, the radiation is actually constrained with this hypothesis, with these postulates. Electron cannot radiate energy when it revolves around the nucleus. Okay, number 2 is when electron revolves in any orbit, its angular momentum is quantized. That means its angular momentum have some specific values corresponding to their orbits. Okay, when the electron revolves in the first orbit, then its angular momentum would be in h by 2 pi, and when it revolves in the second orbit, then it is this is a first orbit is a in any orbit this is actually nh by 2 pi. Okay, in any orbit this is actually nh by 2 pi. For nth orbit this is actually nh by 2 pi. So first orbit angular momentum is h by 2 pi. Second orbit it would be 2 into h by 2 pi. Then third orbit it would be, and so on, 3h by 2 pi, and so on. Okay, the angular momentum expression, you can also write angular momentum as this is the momentum, linear momentum, and when the electron revolved in the circular orbit, when an object revolved in the circular orbit, so angular momentum is nothing but a linear momentum into the radius. This is the angular momentum, and that expression would be nh by 2 pi. If you specify it more correctly, if you express it more correctly, then you have to mention mvn rn. mvn into rn. This is more specific presentation. Means your orbit is the nth orbit, so rn is radius of the nth orbit, and vn is the velocity of the electron in the nth orbit. So this is actually quantization formula, quantization of the angular momentum. And the third orbit, which is the third postulate, is about the radiations. Okay, emission spectrum. So electron when jump from high orbit to low orbit, suppose this is n is equal to 2 and this is n is equal to 3. So this is the higher orbit, this is the lower orbit. So there is n is equal to 1. So when electron jump from 3 to 2, then electron. Okay, one more thing is that. These are the orbits, the energies of these orbits are increasing. Okay, increasing. Suppose if this energy is minus 10, then it would be minus 6, then it would be minus 4, then it would be minus 3, then minus 1, etc. So energy is increasing. Okay, energy increases when the principal quantum number increases. Okay, as you move away from the nucleus, so energy increases. So this is actually the first orbit. For example, this energy is minus 10, so this is actually lowest energy state. Then this is higher than this, then this is higher than this, and according to this energy increases. So when electron jumps from the higher orbit to lower orbit, so difference of energy radiates as the electromagnetic spectrum. So suppose this is the initial orbit and this is the final orbit, so difference of energy, so this is a high energy, this is a lower energy when electron jump from initial to final. Let's say in this example, this is initial, this is final. When electron jumps from initial to final, and the difference of energy is radiate as a spectrum of frequency nu, so energy h nu. From that expression you can also calculate the wavelength. It is in this expression, nu is equal to c by lambda, so h nu is actually c by lambda. So this delta E is actually c by lambda, from where you can easily calculate the spectrum wavelength. This delta E is actually the difference of energy between the two states, difference of energy between the two levels. Okay, levels can also be defined as a state. So difference of energy between two states. Okay, principal quantum number actually define the states of the electron. So these are all about the Bohr's postulates. Okay, so now you can do in my last class actually I did these calculations, but as you all know, the Deepti was absent in the last class, so I have to repeat the class. Actually I have recorded, but the sound quality of the recording part of it is very bad, so I couldn't actually, but you can say I didn't actually uploaded the video because the quality of the sound is very low. Now so that's why I repeat the class. Okay, so suppose this is your nucleus, so positive charge. So Z is the atomic number of the nucleus. So Z is the atomic number of the nucleus, atomic number. Okay, suppose this is your first orbit, so this is your second orbit, this is your third orbit. So for example, say this is your nth orbit. Okay, so this is your nth orbit. It may be first orbit, second orbit, third orbit, fourth orbit, etc. So for simplicity you say, so order of the orbit is n. So an electron exists, or an electron present over there, and electron revolve around the nucleus around the positive charge in a circular orbit of radius Rn. Now I use Rn as R. In my last line of the expression I substitute R by Rn. Okay, if I carry Rn throughout my expressions, throughout my calculations, it would be some complications will arise. So that's why I just simplify, I just represent Rn as R, and in my last expression I substitute R by Rn to show the radius of the nth orbit. Okay, so first suppose this is an electron is over there, so this is positive charge of charge Jd, this is the radius of Rn. Electron is revolving around the positive charge, and you know that with a velocity v, okay, with a velocity v. So to rotate in the circular orbit you need centripetal force, and that centripetal force is mv square 1 minute. So the required centripetal force is mv square by r. Okay, mv square by r. Again, this is the velocity in the nth orbit, but for the simplicity I use Vn as n, Vs as V only, and in my last expression I use replace this V by Vn. Okay, to show you this is the velocity of the nth orbit. Okay, So the centripetal force required to move in a circular orbit is mv square by r, and that centripetal force is actually supplied by the Coulomb attractive force, because this is a positive charge, this is a negative charge. So positive charge attracts the negative electron to the center, and that attractive force is given by q1 q2 by r square. And in SI unit you have to write 1 by 4 pi epsilon as a constant. Okay, so your expression now becomes same v square, and that r square cancels, so v square r is equal to 1 by 4 pi epsilon naught into jd square. So jd square divided by 4 pi epsilon naught. So this is number 1. Now again use your Bohr's postulate, actually second postulate. Okay, what is the second postulate? The angular momentum is nh by 2 pi. That means angular momentum in the nth orbit, in any orbit, is quantized and depends on the principal quantum number. Actually the principal quantum number times h by 2 pi. So m vn rn, okay, not vn, I again repeat. So vn is actually replaced by v for the simplicity, so nh by 2 pi. So this is your actually angular momentum in the circular orbit. So from that two expression you can easily calculate the radius. How? Just squaring 2. So m square v square r square is equal to n square h square by 4 pi square. That's why 2 divide 1. So 2 divide 1 you will get m r, because this is m v square r and this is m square v square r square. So if you divide you will get m r. Okay, now v square cancel. There is 1m, this is m square, so 1m cancel, so 1m is there remaining, and r and r square, so there is only m into r. Okay, if you can't understand, so let's do it in expanding this form division. M square v square r square divided by m v square r is z square, first is n square h square, first number 2. So this is your number 2. Okay, this is not number 2, this is number 2. So n square h square by 4 pi square, and there is jd square over 4 pi epsilon naught. Okay, so 4 cancel, pi cancel, so it would be epsilon naught n square h square by pi z e square. Okay, then r m v square cancel, 1m 1r cancel, so only m into r, that is equal to epsilon naught n square h square pi z e square. So r is epsilon naught n square h square pi m z e square, and as I have mentioned you, I just replace r by rn to show this is actually radius of the nth orbit. Again for hydrogen, this is actually the main formula, and for hydrogen your z is equal to 1 and your value would be rn epsilon naught n square h square pi m e square. And for fast orbit, for hydrogen atom, the fast orbit, okay, r1 is equal to epsilon naught h square and pi m e square. If you put the all values, because in the expression these all are constant, epsilon naught, epsilon, the value of epsilon naught, h, pi, m, mass of the electron and charge of the electron. If you substitute all these values, you will get 0.53 into 10 to the power minus 10 meter, and that is actually 0.3 Armstrong. This is the radius, okay, of the first orbit. This is the radius of the first orbit, and this orbit is also known as a Bohr orbit. That means radius of the first orbit, that means first orbit of the hydrogen atom is called the Bohr orbit, and that is represented by a0. So putting over here, your expression would be Rn is equal to n square a0. This is for hydrogen, and for any other atoms, Rn is equal to n square by z into a0. This is for any other atom. Okay, and this is for hydrogen atom, because for hydrogen z is equal to 1. So putting z is equal to 1, you will get this expression. So this is your values, and this is your calculations for the radius. Now we'll do some calculations for determine the velocity in the nth orbit. Okay, for the velocity, what do you have to do? Velocity, how do you find the velocity? How do you find the velocity? Okay, so this is one. Now say this is your expression, and this is using these two expression, then you will get the velocity, na? In one you have mv square r, in two you have mv r. So if you divide this, mv square r divided by mv r, simple, you will get the velocity. So mv square r means j square by 4 pi epsilon naught into, and you have in mvr is nh by 2 pi. So this is 2 cancel, cancel, r cancel. So your value would be z square 2 epsilon naught n h. Okay, mv square r is z square by this, and mvr is nh by 2 pi. From that you can calculate the v. Okay, so this is v. So v is equal to v square not, there is one v in the denominator, so v cancel, so only v is z square by 2 epsilon naught n h. This is the velocity. So actually this is the velocity of the nth orbit. So vn z square by 2 epsilon naught n h. Okay, this is the velocity. So the velocity of the first orbit, velocity in the first orbit for a hydrogen atom. Okay, now for hydrogen atom it would be your expression again. For a hydrogen atom কি করতে হবে? Your expression is just put z is equal to 1, then square by 2 epsilon naught n h. Okay, now suppose the velocity in the first orbit is square by 2 epsilon naught h, then the velocity of the nth orbit would be v1 by n. Okay na? Because this expression is the velocity in the first orbit, so without n the remaining portion is the velocity in the first orbit. So velocity in the nth orbit is nothing but velocity in the first orbit divided by n. That means as you move away from the nucleus, that means as you goes away from the nucleus, means first orbit to second orbit, your velocity decreases, second orbit to third orbit, your velocity again decreases. So as you move far away from the nucleus, the velocity corresponding in that nucleus in the orbit decreases. Okay na? So velocity in the first orbit is higher, the velocity in the second orbit and third, fourth, fifth, etc., the velocity decreases. Okay, so there is a relation between these two. There is a very good understanding, mathematical understanding. If you are interested, then I can show you mathematically. There is a very good mathematical relations between two. Okay, just try to understand. This is the velocity of the electron. So what would be the momentum in the first orbit? So this is the momentum of the electron in the first orbit, that nothing but m square by 2 epsilon naught into h. Now doing the calculations, what would be the result? Just do the calculations, putting the all values. M is 9.1, 10 to the 31. I am very actually interested to do the calculation. Okay, I like to do the calculations all the time because number fit my mind very easily. Figures, these numbers, and this h is 6.624 into 10 to the power minus 34. Doing the calculations, what you'll get? So this is 9.1, so 9.1 into 1.6 square into 1.6 square. Okay, 23.296 divided by 2 divided by 2 is equal to eto divided by 8.8/4, 8.854 is equal to eto divided by 6.624 divided by 6.624, and your result is 0.198. That means 0.199 into 10 to the power minus 31 minus 19 32 38. So in the ups, the numerator, this is minus 38 minus 31, and there is the denominator minus 12. When it comes to the numerator, it will be plus 12 and plus 34. Okay, this is 46, this is minus 69, and if doing the calculation you will get 3 2. So this is your minus 23. So this is your minus 23. This is the momentum in SI. Then what is the wavelength associated with the electron in the first orbit? So wavelength associated with the motion of the electron in the first orbit, because as you know, by de Broglie, the electron is a very tiny particles, so its motions can be defined as a wavelength. Its motions, it has a wave nature, and the wavelength of the electron, moving electron, can be defined by using de Broglie formula. Lambda is equal to h by p. So lambda 1 is equal to h by p1. H is 6.624 into 10 to the power minus 34, and p1 is 0.199 into 10 to the power minus 23. Your result is 6.624 exponential minus 34 divided by 0.199. Your result is 33.2 29 into 10 to the power 29, 10 to the power minus 11. That means 3.33 into 10 to the power minus 10 meter. This is your wavelength. Now you see the radius of the first orbit is 0.53 angstrom for hydrogen, and this is the velocity of the electron, and this is the wavelength associated with the electron in the first orbit. Now what is the perimeter of the first orbit? If this is a radius, then what is the perimeter? So perimeter is that means total length of this first orbit, that is called the perimeter. The perimeter, that means total length of the first orbit, is nothing but 2 pi r, means r1. So 2 pi into 0.53 angstrom means 10 to the power minus 10. So 2 into ship pi into 0.53. Your result is 3.33 into 10 to the power minus 10 meter. You know, this wavelength is equal to the perimeter. Then what does it mean? It means that means in this length, total one wavelength is associated in this length of the first orbit. That means the total first orbit, the length of the first orbit, is actually associated with a single wave. You know, in a single wave there is a trough and there is a crest. This is a single wave. If this length is straight, then this is a single wave. But if the path length is circular, then this would be your crest and this would be your, okay, so it would be like this. So in the first orbit there is a one wave. Similarly for the second wave, in the second orbit there are two wavelengths will be fitted. Okay, now two wavelengths. So in this half there is a single wave, then the remaining half there is another wave. Okay, so in the third orbit, so this is n is equal to 1, only one crest and trough. This is n is equal to 2, so there are two waves associated, fitted in the second orbit. In the third orbit, okay, that length of the third orbit would be such that actually there are this 1 2 okay 3. So there are three waves. Okay, this is wave number 1, this again wave number 2, and this again wave number 3. In this way Bose actually can able to show these calculations. Okay, so the path length is very interesting. The path length of the first orbit is such that there is only one wave associated in this orbit. In the second orbit, there are two waves. So this is wave number 1, and this is wave number 2. In the third orbit, the length of the third orbit is such that in this orbit only 3 waves associated in this orbit. So number of principal quantum number of the wave is actually the number of de Broglie wave associated with that orbit. Okay, so this is your so up to that we derive the velocity. So this is actually velocity and this is actually radius. We derive velocity, we derive radius. Okay, now we derive velocity, we derive radius. So this is the radius, this is the general expression of the radius for the hydrogen atom, and this is the radius in terms of Bohr orbit, Bohr radius. This is the velocity, this is the velocity in the nth orbit, and this is in terms of velocity in the with respect to the first orbit. Okay, no? Velocity in the first orbit divided by n, then you will get the velocity of the remaining orbit. So velocity, radius calculations are shown. Now I will do some calculations for the energy in the nth orbit. Okay, next our topic is to find the energy associated with the nth orbit. Energy associated with the nth orbit using Bohr's postulates. So our starting calculations equations are same. mv square by r is z square by 4 pi epsilon naught r square, and this is equation number 1. And your angular momentum mvr is nothing but nh by 2 pi. Okay, now so just simplify it. V square is equal to z square by 4 pi epsilon naught into r. So kinetic energy with the nth orbit is nothing. Kinetic energy is half mv square. So kinetic energy associated with the electron, half mv square. Half mv square is z square 8 pi epsilon naught into r. Actually I am calculating the kinetic energy in the nth orbit. Okay, calculate to show the kinetic energy in the nth orbit. Actually the correct expression would be half m vn square z square by 8 pi epsilon naught rn. But as I have mentioned you earlier that I will not write vn and rn in the process, but in the last expression I will write substitute the values, required values. Okay, so putting the values of radius, you know, z square 8 pi epsilon naught, and what is the radius? This is actually radius of the nth orbit. This is actually radius of the nth orbit. This is actually radius of the nth orbit. So putting the values of radius in the nth orbit for any atom. Okay, what is the expression? Okay, radius of the nth orbit is epsilon a. This is epsilon n square pi z. What is the radius? Radius is epsilon naught n square h square pi m z square. So this is the expression radius. Using this value, epsilon naught n square h square pi m z square. Okay, epsilon naught n square h square pi m z square. Carry this expression over here. So epsilon naught n square h square pi m z square. So pi cancel. So it would be m e to the 4 z square divided by 8 epsilon naught square n square h square. This is the kinetic energy of the nth orbit, and you can write it as Ek. So this is the kinetic energy of the electron in the nth orbit. Okay, m e to the 4 j square 8 epsilon square n square h square. Now, since the electron is revolving under the influence of the Coulomb force, the attractive force by the nucleus, that means electron is revolving under a force. A force means there is a potential. Attractive force means potential energy is negative. This is the concept of the from that we have developed in our electrostatics. Okay. Since the electron is revolving under attractive force gives the required centripetal force to revolve the electron in the orbit. So, since the electron is in the force field, so electron possesses some potential energy, and as it is in the as it is under attractive force, the potential energy would be negative. So your potential energy is negative. What is the value of the potential energy? So let's find from the simple expression. Suppose this is a charge JD, and you have a charge over there, and this is a E. So the potential energy of the system is potential energy Q1, Q2. So this is minus E. So Q1, Q2 by 4 pi epsilon naught into R. This is the potential energy of the system having separation R. So that is equal to minus Z E square by 4 pi epsilon naught into R. This is the potential energy of the system. So why negative? Because this is positive, this is negative. So this electron is attracted by the positive charge. That's why the potential energy is negative. So similar here, the potential energy of the electron when it revolves around the positive nucleus in an orbit of radius r is, so the separation between the positive charge and electron is also r. Similar here, so use this expression for the potential energy. So minus Z E square by 4 pi epsilon naught into r, and again you substitute the values of r. Actually this is a nth orbit, so it would be your Rn. More specifically, it would be your Rn. So write the expression of radius of the nth orbit. So minus Z E square divided by 4 pi epsilon naught into Rn, and Rn is epsilon naught n square h square pi m Z E square. So pi cancel, so your expression is a minus a e to the 4 Z square by 4 epsilon naught square n square h square. This is the potential energy of the electron in the nth orbit. Minus m e to the 4 Z square 4 pi epsilon naught square pi cancel, so you know this pi will not be there, this pi is cancelled. So 4 epsilon square n square h square. So total energy, so better clear this portion. So total energy of the electron in the nth orbit, total energy E is nothing but nth orbit, so En is nothing but sum of the kinetic energy plus potential energy. Electron have same have the two parts, kinetic energy and potential energy. Such the values, kinetic energy is m to the 4 J square 8 epsilon naught square n square h square minus actually plus, and your value is minus e to the 4 Z square 4 epsilon naught square n square h square. So your result is actually if you do multiply numerator and denominator, your expression now becomes this is become 2 and this is 8. Actually earlier it is 4, now multiply numerator and denominator both by 2, so it is 2 and it is 8. So plus and minus is minus, so m e to the 4 J square divided by 8 epsilon naught square n square h square minus m e to the 4 j square 2m raised over j square divided by 8 epsilon naught square n square h square. So your result is minus m raised to 4 j square divided by 8 epsilon naught square n square h square. So this is the radial energy of the electron in nth orbit. For hydrogen, we do this calculations specifically for hydrogen, because in our syllabus only hydrogen atom is there. So do calculations for the hydrogen. So Z is equal to 1 only. So En for hydrogen is nothing but a to the 4 by 8 epsilon naught square n square h square. So for n is equal to 1, your expression is E1. So minus m, that means energy associated with the first orbit 8 epsilon naught square h square. So En, what would be the value of En? En is nothing but this is E1 by n square. Okay na? E1 by n square. Okay, just leave this portion n. The remaining portion gives you the value of E1. So En is E1 by n square. So this is the expression of the energy in any orbit. Now what will be the value of the energy associated in the first orbit? So just substitute all this value, 9.1 into 10 to the power minus 31 into 1.6 into 10 to the power minus 19 all to the power 4 divided by 8 into 8.854 into 10 to the power minus 12 into h square 6.624 into 10 to the power minus 34. Again I repeat the number. I like the number digits. So its value is minus 13.6. You do calculations by yourself using calculator. You'll get this result, minus 13.6 into 1.6 into 10 to the power minus 19, this much joule. And if you divide this result with 1, oh, this is 1.6. If you divide the result with 1.6 into minus 19, your expression unit will convert to electron volt, and you cancel this term, you will get minus 13.6 electron volt. So energy associated with the first orbit is minus 13.6 electron volt. Then your nth orbit energy is minus 13.6 divided by n square. Okay, this is energy in the nth orbit. Energy in the nth orbit. So for the first orbit is so for first orbit n is equal to 1. Here energy is minus 13.6. For second orbit n is equal to 2. Energy is minus 13.6 divided by 4, because 2 square, because n is 2, minus 13.6 divided by 2 square means 4, minus 13.6 divided by 4. Your result is minus 3.4 electron volt. So difference is 10.2. Second orbit is 10.2 electron volt higher than the first orbit. Okay, second orbit is 10.2 electron volt higher than the energy of the first orbit. So second orbit is excited, first orbit is ground state. Okay, now for n is equal to 3, your energy is E3, and yet E3 is minus 13.6 by n square means 3 square. So 13.6 divided by 3 square means 9, and your result is 1.51 or 1.511. So minus 1.511 electron volt. Again, the difference between two states is 3.4 divided by minus, so 1.51, so 1.89. Again, the gapping between the two orbits energy level difference is decreases very much. Okay, so energy difference between first and second is 10.2 electron volt. Between second and third is only 1.89 electron volt. Now n is equal to 4. You have E4. E4 is minus 13.6 divided by 16. 13.6 divided by 16. Your result is 0.85 electron volt. So 0.85 electron volt. Again, the difference now between third and fourth is 1.51 minus 0.85, 0.66. Again, the separation, energy separation, not the separation, actually this is the energy separation. So energy separation decreases as you move to the higher orbits. Again, you see that the energy associated with the first orbit is minimum minus 13.6. As you move higher orbits, where energy associated with the orbits increases. 13.6 minus 3.4 minus 1.51 minus 0.85. Okay, for n is equal to 5, and just use put the values of n, you will get the energy, corresponding energy of the orbits. Okay, so in this way you can calculate the energy associated with orbits. So okay, next we derive some formulas between kinetic energy, potential energy of the electron in the orbits. So let's see what is the expression. So kinetic energy expression is kinetic energy is kinetic energy is this is kinetic energy m e to the 4j square. This is not for hydrogen. If you do the calculation if you want to do the calculation for the hydrogen, just substitute z is equal to 1. Your total expression transform into hydrogen for hydrogen. So this is the kinetic energy, 8 epsilon square n square h square, and your potential energy is this is Ek, Ke or Ek. Okay, your potential energy is how much? Minus m, this much, minus m e to the 4 z square divided by 4 epsilon naught square n square h square. This is your potential energy. Now if you have you can draw a relationship between kinetic energy, potential energy. How? So kinetic potential energy is actually 2 times kinetic energy, but with a negative sign. Okay, now potential energy is 2 times kinetic energy, because kinetic energy is in the positive, potential energy is negative. So when you multiply the kinetic energy with a negative sign, the total kinetic energy, now this result will transform into negative. Okay, that's why you have to multiply the negative sign. And in the numerator is in the denominator for the kinetic energy there is 8, and for potential there is 4. So if you multiply by 2 with the kinetic energy, then your 8 convert into 4. That's why EP is equal to minus 2. Okay, so this is the relation. So total energy E is equal to EP plus EK. Okay, EP plus EK, kinetic energy plus potential energy. So EP means minus 2 EK plus EK. That means is equal to minus EK. That means this is equal to minus EK. That means total energy is equal to minus kinetic energy. So this is the relations. So these relations are, you have to mention, you have to remember, because you have to there could be some questions from this chapter, from this portions. Okay, now you can explain the emission spectrum for the hydrogen atom. Okay, you can explain the emission spectrum, the wavelength of the emission spectrum for the hydrogen atom using this formula. How? So explain the spectrum of hydrogen atom from Bohr's theory. The question would be explain the origin of different spectrum, from Bohr's theory. That means already from the Bohr's theory, using Bohr's theory, you have derived this formula. That means you can derive this formula as a fundamental equations, as a formula. Okay, this is m e to the 4 z square divided by 8 epsilon square n square h square. So this is the energy of the nth orbit. Suppose this is nucleus and this is nth orbit. So energy associated with that electron is this much. Now suppose electron, suppose this is initial orbit. We are considering 2 orbits. This is initial orbit and this is final orbit. So electron jumps from initial orbit to final orbit. Okay, electron jumps from initial orbit to final orbit. Electron jump from initial orbit to final orbit. So electron energy associated with the initial orbit is nothing but m to the 4 z square by 8 epsilon square ni square h square. Now when it comes to the final orbit, then energy associated with the final orbit is minus m to the 4 z square divided by 8 epsilon square final square h square. So as this is a higher orbit and this is a lower orbit, so energy in this orbit is higher, energy in this orbit is lower. So electron when comes to a higher orbit to lower orbit, so difference of energy comes as a spectrum. So difference of energy is this is a higher orbit, this is a lower orbit, this is high energy, this is low energy. So difference you can calculate, there is EI minus EF, this is a difference of energy. So putting the values EI minus EF, that means EI is minus m to the 4 z square divided by 8 epsilon square h square. So EI means minus ni square. Oh, minus is common. EI minus EF. Okay, just two calculations. So this is ni square, and similarly minus EF means, so it would be your plus, because already F is there is a minus, so minus F means this would be plus m to the 4 z square divided by 8 epsilon square nf square h square. So now the common m to the 4 z square 8 epsilon square h square, your expression would be 1 by nf square minus 1 by ni square. Okay, since it is positive, so it comes first, and it is negative, it comes in the second term. So this is EI minus EF, and this is your difference of energy between the two orbits, and it comes as a spectrum of frequency nu. So it is your h nu. So nu is the frequency of the emitted spectrum. Then what is nu's frequency of the emitted spectrum? M e to the 4 z square divided by 8 epsilon square into h cube, 1 by nf square minus 1 by ni square. Okay, this is the frequency. Now frequency and wavelength is associated by c by lambda, because c is equal to nu lambda, so nu is equal to c by lambda. So this is equal to m to the 4 z square divided by 8 epsilon square h cube, 1 by nf square minus 1 by ni square. Therefore 1 by lambda, therefore 1 by lambda is nothing but m to the 4 z square divided by 8 epsilon naught square c h cube, 1 by nf square minus 1 by ni square. So for hydrogen, z is equal to 1. So it could be your 1. So 1 by lambda is e to the 4 by 8 epsilon square c h cube, 1 by nf square minus 1 by ni square. Okay, this term is known as a Rydberg constant. Okay, for a hydrogen atom. So this is Rydberg constant. So this is Rydberg constant is nothing but m to the 4 8 epsilon square c. Try to find out this value, because this is a constant. M is mass, electron is charge, 8 epsilon square dielectric constant is free space, c is the velocity of light, and h is the Planck constant. Putting all these values, you will get the value of the constant. Now this is your 1 by nf square, 1 by nf square minus 1 by ni square, and this is your 1 by lambda. Now from this expression you can explain how the different spectrums actually come from the hydrogen atom. Why hydrogen atom? Because already I have substituted Z is equal to 1. That means this formula now used for the hydrogen atom. Now, suppose the final orbit is equal to 1. Okay, so the electron comes ultimately to the first orbit, and initial maybe come from second orbit or third orbit or fourth orbit, etc. It can transit from second to first. If the electron is in the second orbit, then it can transit from second to first. If it is in the third orbit, then it can come third to 1. It can comes if anyhow electron jumps up to the fourth orbit, then electron again come to fourth to 1. So electron transition electrons from second to 1 or third to 1 or fourth to 1. This all belongs to Lyman series. This all belongs to Lyman series. Okay. This all belongs to Lyman series. So Lyman series is when the final orbit is 1. That means electron jumps when to the first orbit. So 1 by lambda is R 1 by 1 square, means 1 minus 1 by Ni square. If electron jumps from the second to 1, then means it is 1 by 4 minus 1. That means 3 by 4. Then if the electron jumps from third to 1, 1 by 9 minus 1, 8 by 9. Okay. Okay. So you can write this is your this corresponds to Lyman series. So this is 2, 3, 4, and this is 1. So first Lyman series, first wavelength of the Lyman series, second wavelength of the Lyman series, third wavelength of the Lyman series. Okay, na? These all are Lyman series. Lyman series means electron ultimately jumps to orbit number 1. If somehow electron exists in the second orbit, it can transit to first orbit. Then it is your first Lyman series, first wavelength of the Lyman series. This is second wavelength, third wavelength, etc. Now suppose if Ni is equal to 2, suppose initial orbit is 2, then 1 by lambda is equal to R into 1 minus 1 by, so try to understand it very carefully, 1 minus 1 by 4, R into 3 by 4. This is 1 by lambda. Then what is lambda? Lambda is 4 by 3R. Okay. Now check, if Ni is equal to 3, what will happen? Okay. What will happen if Ni is equal to 3? That means electron transit from third to 1. What will happen? So if Ni is equal to 3, so 1 by lambda is equal to R into 1 minus 1 by 9. So your result would be 8 by 9 R. So your lambda now becomes 9 by 8 R. Okay, which result is higher? This is 4 by 3 means 0. This is greater than 1. Right? 4 by 3 is greater than 1. 4 by 3 is greater than 1. 9 by 8 is also greater than 1. But now compare which one is higher, 4 by 3 or 9 by 8. 4 by 3, 4 divide 3 is 1.33. 9 divide 8 is 1.125. That means this, if it is first wavelength of the Lyman series, if it is second of the Lyman series, then lambda 1 is greater than lambda 2. Okay, so this is the so this wavelength is higher than this wavelength. So as you move, if you transit from fourth orbit, then your wavelength decreases. Okay, your wavelength decreases. So this is actually the highest wavelength of Lyman series. Highest wavelength. Okay. Now, if Ni is equal to infinity, that means if the initial orbit is at infinite distance, that means it would be very much away from the positive nucleus. That means Ni is equal to infinity. Then what would happen? If Ni is equal to infinity, putting the values over here, Ni is equal to infinity, then what would happen? Your result would be 1 by lambda is equal to r into 1 minus 1 by infinity square. If n is equal to infinity, that means the electron initially exists in the infinite orbit. Now it jumps from that orbit to first orbit. Then also it corresponds to Leibniz series. Then your 1 by lambda is r, then lambda is equal to 1 by r, and this is your least result, minimum wavelength. So this corresponds, that means when Ni is equal to 1 to, when the transition 1 to 2, it corresponds to highest wavelength, and transition infinity to, again I make a mistake over here. Transition 2 to 1 corresponds to highest wavelength of the Leibniz series, and transition infinity to 1 corresponds to lowest wavelength of the lambda series. Lowest wavelength. Okay, so this corresponds to highest wavelength, this corresponds to lowest wavelength. You have to remember these things. Okay, this corresponds to highest wavelength from 2 to 1, and from infinite to 1, that means when the just the farthest wavelength, farthest orbit, when electron jumps from the farthest orbit to the first orbit, then you will get the lowest wavelength. Okay, this is the origin of the Leibniz series. Now next come to the Balmer series. So number 2 series is known as the Balmer series. Balmer series will originate. So this is n is equal to 1. This is n is equal to 2. When electron make transition from n is equal to 3 to 2 or n is equal to 4 to 2, these are corresponds to Balmer series. That means initial final orbit is equal to 2. Initial orbit maybe 3, maybe 4, maybe 5, etc. Then you will get the Balmer series, and your formula is 1 by lambda is r into 1 by ni square, 1 by nf square. Okay, na? Initially this is nf square, this is your fundamental equation, minus 1 by ni square. So final 1 by nf square means 2, means 1 by nf square means 2 square minus 1 by ni square. Ni may be 3, 4, 5. Okay, so r into 1 by 4 minus 1 by ni square. This is wavelength of the Balmer series. From this expression you can calculate the wavelength of the Balmer series. So the first Balmer, that means when transition from 3 to 2. So from 3 to 2, this is the first Balmer, and this corresponds to highest wavelength. Highest wavelength. Okay, and infinity to 2 corresponds to lowest wavelength. Lowest wavelength. Okay, and again if you put the values, suppose for the first transition, that means if you put ni is equal to 3, so for the first orbit, so your 1 by lambda is equal to r into 1 by 4 minus 1 by ni, first is 3 by 2, 1 by 9. Then put the values you can calculate the values of r from the previous expression, and you if you substitute all these values, do the calculation, you will get the lambda is in the visible region. The lambda is in the visible region. So Balmer series is in the visible region. That means its wavelength lies between 4,800 angstrom to more or less 6,500 angstrom. Okay, so its wavelength lies between these angstroms, 4,800. That means Balmer series wavelength. So from 3 to 2, it corresponds to this, maybe in higher wavelength, and 4 to 2. So this corresponds to okay. So this is the visible region, and Balmer series have this wavelength. So that's why we say the Balmer series is in the visible region. Maybe the exact result can be calculated, but I say the exact wavelength you can calculate, putting all these, putting the values of R and doing calculations, you can calculate the wavelength associated in this transition. Okay, this is in the visible region. The visible region means this wavelength, you can see the wavelength, waves emission spectra. So this is a Balmer series. Then when transition actually from initial is final ultimately, this is number 3, when final orbit is third orbit and initial would be your 4, 5, 6, etc. That means the transition, electron make transition from 4 to 3 or from 5 to 3 or from 6 to 3, then you will get the Paschen series. This is your Paschen series. Okay, now next is if your 1 minute, next is if your final orbit is 4 and initially is maybe 5, 6, 7, etc., then you will get a bracket series. These all are not in the visible region, so you can't see these wavelengths because these are out of visible region. So if final orbit is 5th orbit and initially is say 6, 7, etc., then you can the series is known as Pfund series, P-F-U-N-D, Pfund series. P is here silent, so your series is Pfund series. So these are the emission spectrum from the atoms. I use hydrogen atom here because Z is equal to 1. So these are the emission spectrum, and this is actually the origin of the emission spectrum. Okay. Next, this is the expression of the nth energy of the nth orbit. So suppose n is equal to 1. So energy with that electron is E1. So for n is equal to 1, energy is E1, and that is equal to minus 13.6 electron volt. Ki holo Shanojit? Minus 13.6 electron volt. So electron first exists over here, first in the first orbit. Now, if the electron move to the infinity, so this is n is equal to infinity. So energy associated in the orbit, that means infinity, is minus 13.6 by infinity square, so that is equal to 0. That means if you bring the electron from first orbit to infinity, that means actually you bring the electron outside the atom. You bring the electron outside the atom. That means you make the atom ionize. That means this is a hydrogen atom. You release the electron from the atom. Now it becomes ionized. So to transfer the electrons from the orbit to outside, that means first orbit corresponding energy is minus 13.6. Outside the atom, that means n is equal to infinity, energy is 0 electron volt. So how much energy you have to supply from the outside? So initially its energy is minus 13.6 electron volt. Ultimately, when the electron is outside the atom, its energy is 0 electron volt. So how much energy you have to supply from the outside so that electron energy becomes 0? So initially it is minus 13.6. Now if we add additionally plus 13.6 electron volt, then the total energy becomes 0. That's why when the electron is in the minus 13.6 electron volt, that means when the electron is in the first orbit, then from the outside you have to supply additional plus 13.6 electron volt, so that the total energy of the electron becomes 0. 0 energy means electron is outside the atom, that means atom becomes ionized. That's why this 13.6 electron volt is called the ionization energy. So for the hydrogen atom, the ionization energy is 13.6 electron volt. That's why 13.6 electron volt is the positive 13.6 electron, not negative. Negative means bound, electron is bound to the atom. So if we apply additional plus 13.6, that this makes the electron total energy is 0 electron volt. 0 electron volt means electron is not now bound with the atom. Electron is now free from the atom. When electron is free from the atom becomes ionized. That's why plus 13.6 electron volt is called the ionization energy. And this actually this calculation for the hydrogen atom, that's why this is called the ionization energy for the hydrogen atom. For hydrogen atom. Now your ionization energy is 13.6 electron volt. So you have your ionization energy is 13.6 electron volt. That means you have to supply 13.6 electron volt outside to the hydrogen atom. Okay, you have to apply 13.6 electron volt outside from the hydrogen atom. So you do have a source of 13.6 electron volt. So what would be the source of getting 13.6 electron volt? What would be your arrangement? Is there any idea to get a 13.6 electron volt so that you can supply that energy to the hydrogen atom to make the hydrogen atom ionized? Yes, right? Do you have any idea what would be the source of 13.6 electron volt so that you have 13.6 electron volt so that you can supply that 13.6 electron volt to the atom, hydrogen atom, so that the hydrogen atom get ionized? So you must have the 13.6 electron volt supply source. What would be the kind of source from where you can get 13.6 electron volt? Harshdeep, bol 13.6 ইলেকট্রন ভোল্ট পাওয়ার কি ধরনের সোর্স তোর কাছে থাকতে পারে? তুই কোনো সোর্স বানাতে পারবি যেখান থেকে তুই 13.6 ইলেকট্রন ভোল্ট পেতে পারিস? পেলেই তো তুই হাইড্রোজেন অ্যাটমকে দিতে পারবি। তো ফার্স্টে তোকে পেতে হবে। ভেরি সিম্পল, কিন্তু এগুলা এমন মানে এগুলা পড়ার ব্যাপার না, এগুলা ভাবার ব্যাপার। জাস্ট তুই চিন্তা করে এমনি বেরিয়ে আসবে। How do you get 13.6 electron volt? So that energy you can.
কোনো রেডিয়েশন দিয়ে?
রেডিয়েশন দিয়ে 13.6 আবার রেডিয়েশনকে মাপতে হবে 13.6 ভোল্ট হলো কিনা। Suppose this is the cathode and this is anode. You make a hole over there. This is positive, this is negative, and you just supply 13.6 volt between these two plates. So make electron comes from the cathode by hitting the cathode. So if electron comes, it will accelerate it to the positive charge, positive plate, and it comes from the positive plate, holes of the positive plate. The kinetic energy of the positive plate of the electron from the positive plate would be 13.6 electron volt. Why? Because the potential difference is 13.6 volt. So when the electron goes from A to B, from the plate A to the plate B, it is attracted by the positive plate. So amount of work done is nothing but charge into potential difference 13.6 volt. That means 13.6 electron volt. In this way, you will get the 13.6 electron volt. So electron will come out from this hole as a 13 with a 13.6 electron volt kinetic energy. And if there is a hydrogen atom, it hit the hydrogen atom and make transition of the electron from the first orbit, and the hydrogen atom get ionized. And বলি স্যার একটা ইলেকট্রন কি কোথায় আছে খুঁজে পাবে? এ যাচ্ছে, একটা ইলেকট্রন হাইড্রোজেন আটমে ঘুরছে, এই সময় এরকম আসছে, এই সময় এখানে আছে, খুঁজে পাবে? So take gas of hydrogen atom. Take a gas of hydrogen atom. In the gas, in that cylinder, there are so many hydrogen atoms. At least one electron, one of the hydrogen atom make transition, make collision with the hydrogen atom with this electron, and make transition of the electron from the first orbit to infinity. That means that atom becomes ionized. Ashdeep, you raise your hand. Do you have any question?
No.
You don't have any question. বুঝতে পারলি প্রমাণ কি বললাম? একটা ইলেকট্রন যদি এখান থেকে আসে, এখানে যদি গ্যাস রাখিস, সো একটা ইলেকট্রন তো গ্যাসের কোনো না কোনো অ্যাটমের সঙ্গে তো হিট করতেই পারে। এবার যদি আরও ইলেকট্রন যদি ঝাঁকিস, তাহলে প্রচুর ঝাঁকা ইলেকট্রন আসছে, অ্যান্ড দ্যার ইজ এ গ্যাস অফ হাইড্রোজেন অ্যাটম। সো প্রচুর হাইড্রোজেন অ্যাটম আছে, সো এরা কারোর না কারোর সাথে ধাক্কা মারবে। সো দ্যাট কী হবে, তাহলে এই টোটাল গ্যাস চেম্বারের মধ্যে টোটাল প্রচুর হাইড্রোজেন অ্যাটম কী হবে, তৈরি হয়ে যাবে। বুঝতে পারছি? দিস ইজ দ্য প্রসেস টু মেক দ্য hydrogen ion. So এখান থেকে আমরা কি পেলাম? So that 13.6 volt is the ionization volt, and 13.6 electron volt is the ionization energy, and this is all about your hydrogen atom and the spectrum. Next we have another spectrum which is called the, so this Lyman series, Balmer series, Paschen series, Brackett series, Foon series, these all are actually emission spectrum. These all are actually emission spectrum, because the electron jumps from the higher orbit to the lower orbit. That's why the difference of energy comes out as a spectrum. Actually these radiations actually emitted from the hydrogen atom. That's why these radiations are called the emission spectrum. Okay, the emission spectrum originates due to the transition of the electron from higher orbit to lower orbit. How? When the electron jumps from the second orbit to first orbit, third orbit to first orbit, fourth orbit to first orbit, it creates a Lyman series. When the electron transit from the third to second, fourth to second, fifth to second, it produces a Balmer series. Similarly, when 4 to 3, 5 to 3, 6 to 3, Paschen series. In this way, Brackett series, Foon series. Okay, na? So these all are actually the transition from the higher orbit to lower orbit, higher energy state to lower energy state. That's why these are called the emission spectra. Similarly, there are some absorption spectrum produced in the hydrogen atom. Means hydrogen atom can produce absorption spectrum. How? Suppose initially electron is in the first orbit. That means this energy is 13.6 electron volt. Okay, so this positive charge. And in the second orbit, electron is not present here, but the energy, energy is there is how much? Energy is in the first or second orbit is 3.4 electron volt. Okay, now there are radiations coming out, actually incident on the hydrogen atom. There are radiations. Some radiations have energy. Some radiations have energy is 5 electron volt. Some radiations have energy E to say 8 electron volt. There are some radiations, incident radiations, where energy is say 10.2 electron volt. There are some radiation where energy is say 11 electron volt. So these are all actually incident. These actually associated with the incident radiations. Now there are hydrogen atom. This hydrogen atom electron is in the first orbit. Now suppose this radiation has this much energy. So electron, what happens? Electron absorb this radiation and goes to second orbit. Okay, electron when in the first orbit, it is minus 13.6 electron volt. Now it can absorb this radiation so that it can jump to the second orbit. It cannot absorb this 5 electron volt, 8 electron volt, 11 electron volt, because if absorb this 5 electron volt, then total energy of the electron becomes, initially this is 13.6, now it absorbs 5 electron volt, it is be minus 8.6, and minus 8.6 corresponds to no orbit. It corresponds to no orbit. That's why it cannot absorb this energy. It can only absorb those energies, those frequencies for which it can exist, or it can transfer itself to some upper energy orbit. Okay, for example, if it is in the first orbit, if the radiations, since the radiations are this much energy, then only from this radiation it only absorbs this much energy, because absorbing this energy only it can transfer to the second orbit. If absorb 5 or 8 or 11, it makes no sense, because when if suppose if the electron absorb this energy minus 11 electron volt, what will be the final energy of the electron? Minus 13.6 plus 11, this is minus 2.6, and minus 2.6, with that energy there is no orbit. So electron will not absorb these energies. It can only absorb those energies for which it can place itself to some higher orbit. Okay, and when if you now place a screen over here, then on that screen all these energies make spot. Only minus 10 point electron volt, these radiations will not produce any spot. That means it becomes a dark one. All radiations produce spot, but this 10-point electron volt will not produce any spot. That means it is a dark one. That means you can say in the spectrum there is some wavelength which is absolutely absent. Why absent? Because that energy, that frequency, that radiation actually absorbed by the hydrogen atom. That's why this radiation is called the absorption spectrum. Absorption spectrum means a spectrum which is absent in the transmission, after transmission from the atom. Okay, understand? So on the screen, all frequencies are present, all wavelengths are present, only those frequencies or those radiations are absent which are absorbed by the atom, so that atom or electron can produce or can shift itself to some higher orbits. Okay, so this is all about your hydrogen spectrum, hydrogen atom. Now there are some questions. I'll say okay. One learning based question is that suppose this is n is equal to 1, now this is n is equal to 2, this is n is equal to 3, this is n is equal to 4. Okay, 1, 2, 3, 4. Okay, now this is a transition, this is a transition, this is a transition. Okay, now this is a transition. Okay, I do some different color for this transition. Okay, great. This is a transition and this is a transition, and I use again another color, blue, and there is another transition. So suppose if electron is here, suppose an electron is over here, then there are 1, 2, 3, 4, 5, 6 different radiations can emit from the atom. So if an electron exists in the fourth orbit, so the question is like that, if an electron exists in the fourth quantum state, fourth orbit, so how many probabilities, how many frequencies or how many wavelengths you'll get from that atom? How many emission spectrum you'll get from that atom? For that, you have to draw this diagram and make transition from 4 to this, then this, then this. If you come over here, then this, then this, or if come over here, then this. Okay, so 1, 2, 3, 4, 5, 6. So there are six transitions, possible transitions are there. So there are, for each transition corresponds to one wavelength. So there are 6 different wavelengths. Okay, there are 6 different wavelengths. Now you can do the calculations by mathematically. How? So number of radiations n is n into n minus 1.
স্যার এখানে 2 থেকে 1 একটা হবে না?
ওইটাই করলাম, এই যে ব্লু কালিটাই তো 2 থেকে 1। আরে এই যে ব্লু কালিটা, আচ্ছা এটা হোয়াইট দিয়ে করে দিচ্ছি আমি। ওকে, now is it visible to you? Okay, so how many transitions you will get if the electron is in the fourth orbit? So n is equal to n into n minus 1 by 2. So 6 into no, sorry, why this 4? This is actually in the fourth orbit. Are yaar. So this is actually in the fourth orbit. So 4 into 4 minus 1 by 2. 1 minute, hold now. So how many transitions, possible transitions are there if the electron is in the fourth orbit? So n into n minus 1 by 2. So actually n is a 4 into 4 minus 1 by 2. So 4 into 3 by 2, 12 by 2. So 12 by 2 is called 6. So you use this formula to find the number of transitions. So each transition corresponds to one wavelength. So there are 6 wavelengths, 6 different wavelengths. Okay, so how many wavelengths possible in this transitions when the electron is in the fourth orbit? So there are 6 different wavelengths, 6 different frequencies. Okay, so this is number 1 solution. So there may be some other questions regarding on this topic. In this topic, which transitions corresponds to the emission radiations of maximum wavelength? Now you tell me which transitions corresponds to maximum wavelength. You tell me which radiations corresponds to maximum wavelength. Anyone please? Primankur, Dipti.
Sir, 2 to 1.
2 to 1. Hey Dipti.
2 to 1.
Dipti. Hey, you switch on your video. তো হুইচ আবার বলবে কি আমার ভিডিও সুইচ অন হচ্ছে না ও যা ইয়েস স্যার ওকে স্যার হুইচ ট্রানজিশন corresponds to maximum wavelength or frequency? Maximum wavelength. Actually 2 to 1. Why? Justify your answer. হ্যাঁ সনিজিৎ বলো, জাস্টিফাই করো।
তো কারণ এখানে এমিশন স্পেকট্রাম ওইটা এখানে কমে যাবে, এখানে মানে 2 থেকে 1 করে যেটা হবে 3 থেকে 1 ওইটা আরো কমে যাবে।
এইভাবে বললে তো হবে না, তো কমে যাবে বলেই তো বলছিস যে কম, তো জাস্টিফাই তো হলো না। তুই অ্যান্সারটাকে একটু অন্য ভাষায় বললি, জাস্টিফিকেশন হলো না। তো প্রমাণ করুন বলো তো। অর্ক, হর্ষদীপ,
2 থেকে 1 হবে।
কেন? জাস্টিফাই কর।
মানে প্রথম অবিট থেকে মানে শেল যত
সো ফর 4 to আমাকে বলে দিই 4 to 3 this transition is minimum, energy difference is minimum. That's why since the energy difference is minimum, there's a frequency is minimum and wavelength is maximum. Okay, by then